Okay, so 2.3 is on finding volumes with cylindrical shells. Okay, well, let's work on that. So volumes, 2.3 volumes with cylindrical shell. Okay, area of a cylinder is A equals 2 pi RH. Okay, where R is the radius, okay, and H is the height. Okay, so R is the radius of the cylinder and H is the height of the cylinder. So if we were to look at a cylinder and we were to unwrap the cylinder, okay, we would get, well, let's draw an axis first. Okay. And let's draw a cylinder. Okay. Let's draw my friend the cylinder. Let's draw a better one. My friend the cylinder. There we go. Okay. So Mr. Cylinder. Okay. Okay, if I were to unwrap, if I were to slice this cylinder, okay, and unwrap the cylinder, this cylinder has a radius of R, and it has a height of H. Okay, and if I were to unwrap it, I would get a rectangle. Okay, kind of think of it like the label on a can. If you were to rip off the label on a can or on a bottle, it would end up being a rectangle. The width of the rectangle would be the circumference of the circle. So the circumference. Anybody remember what the circumference is? What the formula for circumference is?
Is it 2 pi RH?
It's 2 pi r, just for circumference. That's this piece here, right? So the circumference, the distance around the circle, is 2 pi r. So this is 2 pi r. Okay. The h is the height of the label. That's h. And so the area of this thing is 2 pi r times h, because the area of a rectangle is just base times height. Okay, just the two dimensions multiplied together. So that's the area. Okay, the volume of a cylindrical shell okay, this has a width to it, a depth to it. And so the depth means that it's a shell. So this is has an inside and an outside now. Okay. And it has a width or what we would call a three-dimensional depth to this shell. This is a cylindrical shell. And then we're going to pack these shells in on each other, shells upon shells upon shells to get our solid. Okay. We're going to say, okay, well, the R is variable. It's going to vary. Okay. And so there'll be some relationship to R and X and H and X. Okay. And so this thing now becomes a solid. Okay, and we say that the width of this, okay, is delta R. Okay. So the volume of the cylindrical shell, okay, so it's a infinitesimal. Okay, that width is going to get, and we're going to take a limit on this thing, and it's going to get smaller and smaller and smaller and smaller until basically delta R goes to 0. And so the volume of the cylindrical shell is V equals 2 pi RH delta R, because we're adding that third dimension. We're saying, oh, okay, well, that third dimension, that delta R, maybe I should move this up. I'm not writing on my, maybe I'll move it down. Okay, and so we have this width, delta R. And if we were to wrap that around, we're at our cylindrical shell, and those, we're going to get shells upon shells, and they're going to build. Okay, then I'm going to get, you know, another shell out here to build my solid, and then we're going to let the distance, that delta R, go to 0. And then so it's going to compact. Again, we're using the idea of infinitesimals here, that we can have an infinite number of shells in a confined space. Okay, because as delta R goes to 0, then this just becomes an infinite sum. And how do we deal with infinite sums? Integration. Okay. Okay, if I have a function, okay, of x, call this f of x. Okay, and we're out here x, and we want to say we want to go from, I don't know, from A to B. Oops. Okay, we want to go from A to B. We're going to put these bands, I'm going to put them in black actually, because these are our barriers. We want to go from A to B. Okay, x is going to vary between A and B. So A is less than x, which is less than B. Okay, less than or equal to B. Okay, and what we're going to do is we're going to say, well, we're going to build an infinite number of cylindrical shells. Okay. And each of these buddies, okay, is going to create, okay, a cylinder. And then we're going to pack those cylinders, an infinite number. We can pack as many as we want here of these infinite number of cylinders. Okay. Inside each other with variable heights. Now, what is the height going to be? Well, to find the volume of this, the volume of all of these shells, okay, the volume, okay, we need to integrate from A to B of all of the cylindrical shells. Okay, so that was 2 pi r, but what's the radius? The radius is varying with respect to what variable? The radius is varying from A to B That's the radius. The radius is varying from A to B with respect to X. So we say, okay, this is 2 pi X. Okay, and that represents R. Okay, this is the radius. And then what's the height? How do we find the height of, if we're out X, then what's the height?
The y value?
Yeah, which is f of X, right? So that's going to be f of X. So that's the height. And then we're going to integrate and we're going to sum up all of these individual cylindrical shells, an infinite number of cylindrical shells, and that's going to give me a solid volume. And so we're going to use the power of integration to sum all of that up. So we get these kind of nested. Before we were taking slices, and we add up an infinite number of slices to get our volume. Here, we're going to add up an infinite number of cylindrical shells to get our volume. Okay. So this is as a, I'll just write it again, and then this is a one. Either got a little slow there. Okay, and this is the method of cylindrical shells. Okay, to find the volume. Of a solid of revolution. Okay. Okay, so let's try this one. Okay, let's try using the method on a region. Number one, find the volume of a solid obtained by rotating the region bounded by y equals 0 and y equals 2x squared minus x cubed about the y-axis. Okay, about the y-axis. So this method is really good if we're finding things about the y-axis. Okay, if we're doing things about an axis that is vertical, this is a really good method because we don't have to change variables. Okay, so this lends itself really well to revolving about the y-axis. Okay, so we first need to figure out, well, what are we dealing with? We're dealing with some sort of cubic, okay, and the y-axis bounded by this cubic and the y-axis. Okay, so we need to find out, well, where do they intersect? Okay, where does the where does the x-axis and y equals 2x squared minus x cubed, where do they intersect? So we're just gonna set them equal to each other. 2x squared minus x cubed is equal to 0. Okay, try to get the endpoints. Okay, and so if I factor out an x squared, I get 2 minus x equals 0. Okay, and so that tells me that x equals 0 or x equals 2. Okay. So if I were to look at a graph of this, we would only really have to graph the thing from 0 to 2. Okay, that's 0. This is 1, and that's 2. Okay. So now what is happening between 0 and 2? Well, at 0, we're getting 0. At 2, we're getting 0. What happens at 1? If I plug in 1 here, I get 2 minus 1, which would be 1. Okay. And so what we would get is we would get this cubic. Okay, it's not the whole thing. It's just from 0 to 2 that I'm graphing, but we get this cubic. Okay, it would have some symmetry over here as well, and it would go up like that. Okay, but we don't care about this part over here. Okay, we just care about this part here. Okay, and we want to revolve this about the y-axis. Okay, again, we don't really want to have to solve this thing for x and put it in terms of y, because that's going to be pretty difficult, especially with an x cubed, right? We've got this x cubed and this x squared. How are you going to solve that for x? It's going to be difficult. So we're going to use cylindrical shells to make it easier. Right? So we're gonna build our cylindrical shells here. Right? I'm just going to show one shell, but know that we're building an infinite number of shells from 0 to 2. Okay, and so this is going to be equal to, okay, the volume is going to be equal to 2 pi, from 0 to 2 of 2 pi times x, the radius is x. Okay, the radius is x, and then the height is f of x. Okay, but what is f of x? F of x is y equals 2x squared minus x cubed dx. Okay. Let's pull out the 2 pi, put that in front. That's just a constant. Let's distribute the x. We get 2x cubed minus x to the 4th dx. Now we can integrate. Okay, this is going to be 2 pi times, this is going to be 2/4 x to the 4th minus 1/5 x to the 5th. Okay, evaluated from 0 to 2. Okay, plugging in, we get 2 pi times 2/4, that's just 1/2, 2 to the 4th power, minus 1/5, 2 to the 5th power. All of that is going to be minus 1/2 0 to the 4th power, minus 1/5 0 to the 5th power. Okay, these zeros are going to go away. 2 to the 4th is 16, and divided by 2, that's 8. Okay. 2 to the 5th is 32 over 5. 8 times 2 pi. This is 8 is 45ths, so that's 45ths minus 32/5 times 2 pi. 40 minus 32 is 8/5 times 2 pi. So this becomes 16 pi over 5. Okay. Okay, and so that will give us this guy rotated. Okay, and okay, kind of look like a donut. So, okay, if we were to rotate the whole thing around and we get the total volume of that donut, kind of like a donut with a missing hole. Okay, let's try one where we have two functions. Right? Okay. Number 2, find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. Okay. That's y-axis, sorry. Y-axis. Okay. Rotating about the y-axis, the region between y equals x and y equals x squared. Okay, so again, y-axis kind of lends itself to cylindrical shells method. I do need to find the endpoints. So let's set x equal to x squared. Okay, let's toss x squared to the other side. X minus x squared equals 0. Factor out an x, I get 1 minus x. And so we know that x is equal to 0 and x is equal to 1. Okay, so x is going to go from 0 to 1. Okay, what's this thing look like? Well, it's just my parabola and my line y equals x. And so we're going to rotate this thing, this little slice. Okay, we're going to rotate this thing about the y-axis. Okay, and we're going to get a solid revolution. Okay. But we're going to use cylindrical shells to help us get that solid revolution. Okay, all these nested shells, they're called. Okay, so what do we got to do? Well, we've got to figure out what is R and what is H. Okay, what is R and what is H? So R is just going to be X. Let me zoom in on this picture here that I've drawn. Okay, let me use black to help me figure out what's going on here. Okay, so R is just some X value. Okay, so I'm just going to go out some R, some X value, and H is actually going to be the height of this slice there. That's H. Okay, for that X value, for that radius, we're going out to this radius, we're going to get a height that starts at X and ends at X squared. Starts at X, ends at X squared. It's between X, y equals X, and it's between y equals x squared. So y equals x right here. This is y equals x squared right there. Kind of looks like a square. Okay, y equals x is there. Y equals x squared is there. So that little slice, that black slice that I have there, the height on that, back over here. Okay, so what's the radius? The radius is x, but what's the height? The height is going to be the top function, x, minus the bottom function, x squared. That's the height of that slice there. I could have blown it up, I guess, if we really wanted to. I could try to make it a little bit more like that. We have this slice, this black slice. Okay, and it's the top function minus the bottom function. Okay, that's the height, that's h. Okay. Okay, between 0 and 1. I'll do a little thing like they do, where it's like, oh, look, this is a zoomed in image of this. Okay. Got some zooming going on. Zoom on my Zoom. Okay. So we're going to set this up now. This is going to be the integral. Volume is going to be the integral of 0 to 1 of 2 pi, okay, times r. R is my x value times h. H is going to be x minus x squared dx. Another simple integral. Okay, I'm going to pull the 2 pi out in front. I'm going to distribute the x. We've got x squared minus x cubed dx. This is going to be x cubed over 3 minus x to the 4th over 4 from 0 to 1 multiplied by 2 pi. Okay, plug in. We've got 1 cubed over 3 minus 1 to the 4th over 4 minus 0 cubed over 3 minus 0 to the 4th over 4. The zeros go away. And I'm just left with 1/3 minus 1/4 times 2 pi. 1/3 minus 1/4 is 1/12. That's 4/12 minus 3/12, which is 1/12 times 2 pi. The 2 and the 12 cancel to leave me with pi over 6. Okay, for my volume is a pi. Okay. Okay. If no, for a solid rotated about the x-axis, use the disk/washer method. Okay. X-axis, use disk washer method. However, they may ask you to use the shells method. And you're like, okay, well, how do I use the shells method if I'm going around the x-axis? Well, we just have to change the variables. We have to flip the variables from x's to y's. Okay, however, if shells is asked for, then the volume is equal to the integral from c to d of 2 pi y f of y dy. Okay, as c is less than or equal to y, which is less than or equal to d. So again, the default would be if you're given something that's rotated around the x-axis, use the disk method because you don't have to change variables. If it's rotated about the y-axis, use cylindrical shells because you don't have to change variables. However, if they want, you know, if they're particularly asking for the shells method and we're rotating about the x-axis, then you just need to change your variables. Okay. Okay. So number 3. Okay, let me just reiterate that one more time. So rotate about the x-axis use disks washer as default. Rotate about the y-axis, use cylindrical shells as your default. But the problem may ask you, hey, do this one, rotate it about the y-axis using disks, or do this one, rotate about the x-axis using shells. Right? Again, you know, if we're doing disk method, say that we have a function, okay, maybe y equals x squared, and we want to rotate about the y-axis, that's shells. But if we have this now function here, and we want to rotate about the x-axis, not a very good parabola. We want to rotate about the x-axis. Okay, that's disks. Okay, we're going to slice it up using disks. So, bubbles. Yes. Okay. Because then we can just use x and f of x. Okay, we can just square f of x and we get our answer. Here we just use x f of x if we're rotating about the y. We don't have to solve for the other variable and then try to figure out what the limits are. Okay, but let's just say that we're feeling spicy and we want to use cylindrical shells to find the volume of the solid under the curve y equals radical x for x going from 0 to 1 rotated about the x-axis.
Do you mind if I ask a question real quick?
Yeah, go ahead.
Thank you. Is it more about like the orientation of where you're rotating? Like if you were like rotating around x equals 1, would you use the cylinder method or does that not work out that way?
Yes, if you are, if it is the orientation, thank you, Corey. So if you're rotating about a vertical line, shells. If you're rotating about a horizontal line, okay, discs / wash. Okay, so thank you for clarifying.
Thanks.
Because we will get to an example here in a second where there is an auxiliary line. Okay, and we're gonna be like, okay, well, using this auxiliary line, if the auxiliary line was horizontal, I'd want to use discs. If the auxiliary line is vertical, I want to use shells. Okay, it just lends itself easier to that. Okay, but you can use either one. If you want to use discs, more power to you. Okay, now some functions may lend itself easier to one form or the other. So just keep that in mind. It may be a lot easier to use shells in one case than in another case. It might be a lot easier to use disks, given the function. Okay, you know, given the integration that we're doing, maybe it's a lot easier to integrate an exponential instead of a logarithm, or maybe it's a lot easier to, you know, integrate a power than it would be a radical, which maybe we'll see here in this problem. So it depends sometimes on what the function is as well. But as a general rule, this is my default. This is kind of like my go-to. I go to this first, and then if it doesn't work out, then I'll try the second method. Does that make sense? Hopefully that makes
Yeah.
sense.
Thank
Okay.
you.
Yeah. So, but you can do any of them both ways, depending on the complexity of the function. My little caveat. Okay. So, okay, 0 to 1 rotated about the x-axis of x squared will look like this. Right? So now we're going to we're going to use shells on this. Okay, and so we want to know, okay, what's the radius going to be, and then what's the height of one of my shells? Okay, so R and H, right? What's the radius and what's the height? Okay, so I got to put, so R is obviously Y, okay? But the height, that's going to be in terms of, that's going to be a function in terms of Y. Okay, and it's going to actually go, if this height here, okay, it's going to, well, we'll get there in a minute, but we've got to do some manipulation on the height to make sure it's the correct thing. Okay, what's this function though, in terms of Y? Well, the function was Y equals radical X, right? So if we square both sides, we get X equals Y squared. So this function is f of Y equals Y squared. That's that function. Okay, now I need to see, well, what is Y going from? Well, in the original function, if I have y equals radical x, and I plug in 0 for x, I get y equals square root of 0, then y is 0. So that's at point 0, 0. Right? So if the x value was 0, then the y value is 0. So that's kind of nice. That's 0, 0. Okay. If I plug in 1, y equals the square root of 1, then y equals 1. So this was at 1, 1. So this point here is at 1, 1. So again, we're looking at the y values to get our limits of integration. Okay, our limits of integration go from 0 to 1 because we can let r vary. We can let r vary with respect to y. Okay, this is all now with respect to the y variable. We're letting r vary with respect to y. So r is equal to y. Okay, we could say that f of y is equal to y squared. F of y is equal to y squared. But if I let the height be f of y, I would not be getting the correct height. I would be, if I let the height be f of y, I'd be getting this height here. And I don't want that. I want the part that's inside, not the part that's outside. Okay, I want the part that's inside here. Okay. So, well, where does this guy end? This guy here ends at 1, right? An x value of 1. We can say, oh, okay, this is x equals 1. Well, let's go over here. This is x equals 1, or f of y equals 1. Right? You say, oh, okay, this x equals 1, or f of y equals 1. Okay. And so we have two f of y's. We have an f of y equals y squared, and we have an f of y equals 1. And if we take 1 minus y squared, we should get our height. Okay, I'm going to put that in red. Maybe I'll put it in black. Our height is black here. Okay, so the height is going to be, let me put this as g of y, just so we're not doing the same thing twice. Okay, so g of y minus f of y is going to be my height. So my height is going to be 1 minus y squared. Right? That's going to give me h. Okay, so we've got a x value of 1 minus an x value of y squared. Okay, to give me the height that I'm looking at. Okay, it's a horizontal distance, but it's now in terms of y, not x. Okay, it goes from x equals 1 to x equals y squared. So now let's integrate, given all the information we know. We know that y is going to go from 0 to 1. We know we have 2 pi, and then we have y as our radius. Our radius is going to vary with respect to y. R is going to vary from 0 to 1 with respect to y. Okay. Okay, and then we have 1 minus y squared dy. Pull our 2 pi out in front because it's just a constant. Let's distribute our y. We get y minus y cubed dy. We get 2 pi. Okay, this is going to be y squared over 2 minus y to the 4th over 4, evaluated from 0 to 1. We've got 2 pi times 1 squared over 2 minus 1 to the 4th over 4 minus 0 squared over 2 minus 0 to the 4th over 4. The zeros go to 0. And I'm left with 1/2 minus 1/4. Which is a fourth. Times 2 pi. And so I get pi over 2. Now, we've already done this problem. Compare this problem to 2.2, problem number 2. Okay, here we used disks, okay, to get the same answer. The disk method was a little bit easier, okay, but we came out with the same result. Okay, again, if we're rotating about the x-axis, we would just use disks as our default because it's going to be easier. We wouldn't have to change variables. Okay, and we did do that. We did that as our second problem on the last section. Okay, as creating disks. We said, oh, okay, we've got the square root of x from 0 to 1. Square that, we did one integration, and it came out to pi over 2. This is showing you that you can use shells to get the same result. Okay, the math holds, the center of the universe holds, the math works. Okay. So if you were told specifically, do shells on this one, or do disks on this one, you should be able to do it both ways. Okay, but if you are given a choice, which you will be on the exam, one method may be better than the other. Okay, and again, that will sometimes depend upon the function as well. Okay, let's look at number 4 here. Okay, find the volume of the solid rotated, obtained by rotating the region bounded by y equals x minus x squared and y equals 0, okay, which is the x-axis, about the line x equals 2. Okay, so that's kind of interesting. Okay. Okay, so if we're given a problem like this on the exam, it doesn't say which method to use. Okay, it just says, here's the function. We're rotating about the line x equals 2. And so you could use disks or you could use shells. In this case, as Corey pointed out, because this is a vertical line, shells is probably going to be the easier method, okay, or the preferred method. Okay, I want to try that one by default first. Okay, so. Okay, so what do we got here? We've got a parabola. Okay, let's look at the endpoints of this parabola. X minus x squared and equals 0. Again, we're just going to factor out the x. 1 minus x squared, 1 minus x equals 0. And so the endpoints are x equals 0 and x equals 1. Okay, so x equals 0, x equals 1. Okay, we've got some endpoints there. We've got this parabola. Okay. It's gonna go up a certain height on the vertex. And this is 0, this is 1, and then this is the auxiliary line x equals 2. So this is the x-axis. Okay, so I'm gonna rotate this thing. Whoops. Let's try that again. I'm gonna rotate this thing. Okay. And so I want to get, I want to use my height and I want to find my radius. Okay. So let's look at the radius first. So for the radius, what is the radius? How would I find the length? If I'm out a certain x value, let's call this x, how would I get the radius? The distance from the center of my revolution to my x value. Well, the center is at 2, and then we're out at a certain x value. So wouldn't it just be 2 minus x? Does that make sense? That's that green length there. So 2 minus x. Does that make sense? That's the radius. Okay, what's the height of my cylindrical shells? What's the height of my cylindrical shell here? The height is just going to be f of x. That's just the height. So what was f of x? It was x minus x squared. That's the height. Okay, good. Okay. So now we want to integrate. We want to integrate what? Well, we want to add up all the cylindrical shells created here from 0 to 1. Okay. And then we want to rotate that, okay, 360 degrees. We want to find all the cylindrical shells there. Okay, all the individual shells. Okay, and then find the volume of that solid. This one is going to be a donut. Okay, or the top half of a donut. Okay. Okay, and so let's set up our integral. The volume is equal to 0 to 1 of 2 pi times the radius, 2 minus x, times the height, x minus x squared. Yes. Right? Okay. So let's multiply this out. Let's take our 2 pi out in front. I'm going to FOIL this out. I get 2x minus 2x squared, okay, minus x squared plus x cubed dx. Let's simplify. This is minus 3x squared plus x cubed dx, 2 pi going from 0 to 1. Okay, this is going to be 2x squared over 2 minus 3x cubed over 3. Kind of nice. Threes cancel, threes cancel. This is plus x to the fourth over 4. Evaluated from 0 to 1. This becomes 1 squared minus 1 cubed plus 1 to the fourth over 4 minus 0 squared minus 0 cubed plus 0 to the fourth over 4. Hopefully by now you know the zeros go to 0. Okay, and this is going to be 1 minus 1 plus 1/4. Ones cancel. I'm left with 1/4. 2 pi times 1/4 is again 1 pi over 2. And so the volume of that solid is the same as the volume that we got in the previous problem. It's a different function and it's a different volume, but it just happened to be the same answer. That's kind of a nice result. Okay. Okay. And that is 2.3.